Good morning all. In this class, we will see the Ampere's circuital law, an important law in the field of magnetostatics. Let us discuss about the straight line currents. The magnetic field of an infinite straight wire. The magnetic field of an infinite straight wire is shown in figure. We already know that the magnetic field of a straight wire circles around the wire. If we grab the wire with our right hand with the thumb in the direction of the current, then the fingers curl around the direction of the magnetic field. That is called the right hand rule. Now from Biot-Savart's law, the magnetic field of an infinite wire at a distance s from the wire is given by B is equal to mu 0 I by 2 pi s, where I is the steady current that is passing through the wire, which is constant in magnitude. The magnetic field at a distance s from an infinite wire is given by mu 0 I by 2 pi s. Such fields are drawn in the figure. Now consider a circular path of radius s, and let us evaluate the integral of B around the closed circular path. You just take a circular path of radius s and let us evaluate the integral of B around the closed circular path. The integral of B around the closed circular path is nothing but closed integral B dot dl. That is nothing but closed integral. What is B? Mu 0 I by 2 pi s dl. Here mu 0 I, 2 pi and s are constants, so you can take it outside the integral. Then closed integral B dot dl becomes mu 0 I by 2 pi s integral dl. Now integral dl, that is equal to 2 pi s, the circumference of a circle of radius s. Therefore closed integral B dot dl becomes mu 0 I by 2 pi s into 2 pi s. Thus the integral of B around the closed circular path, closed integral B dot dl, this is equal to mu 0 I, where I is the current enclosed by the circular loop. Now please note that the path of the integration, in the previous case we have taken the path of integration, which is a circular path, and we have arrived at a result closed integral B dot dl, that is equal to mu 0 I enclosed, where we have taken a circular path. But in fact, it does not have to be a circle. The path of integration does not have to be a circle. It can be any loop that encloses the wire. Any loop. If you consider any loop that encloses the wire, and if we take the line integral along that closed loop, then it will give the same answer. How to prove this? To prove, let us use the cylindrical coordinate system. With the coordinate s, phi and z, with the current is flowing along the z axis. You consider the current is flowing along the z axis, then according to the right hand rule, the magnetic field is acting along the phi direction. Now the magnetic field of an infinitely long wire that carries a current I, here the current is flowing in the z direction, that is given by mu 0 I by 2 pi s into phi cap. And in the cylindrical coordinate system, dl is nothing but ds s cap plus s d phi cap plus dz z cap. Now we have b and dl. Now let us evaluate closed integral b dot dl. That is closed integral. What is b? Mu 0 I by 2 pi s phi cap dot, take the dot product with dl, that is ds s cap plus s d phi cap plus dz z cap. If we take the dot product of phi with s, phi dot s 0, phi dot phi is 1, and phi dot z is also 0. So closed integral b dot dl becomes mu 0 I by 2 pi s closed integral b dot dl, that is equal to mu 0 I by 2 pi s, then phi dot phi is 1, so it will become mu 0 I by 2 pi s into s d phi. Now mu 0 I by 2 pi, which is a constant, integral closed integral d phi. Now in cylindrical coordinate system, phi varies from 0 to 2 pi. So the limit of integration is from 0 to 2 pi. And if you do this, you will get closed integral b dot dl, which is equal to mu 0 I. The same answer we are getting for any loop. That is, if we have any loop that encloses the current, then if we integrate, if we perform the integration closed integral b dot dl, then that is equal to mu 0 times the current enclosed by that loop. In the present case, the current enclosed is I. Therefore, closed integral b dot dl equal to mu 0 I. Now consider you have a loop, a closed loop, and there are several wires carrying current which is passing through that loop. In the previous case, we have only one current carrying wire and only one loop. And in the present case, you consider you have a bundle of straight wires and there are several straight wires carrying current that is passing through the loop. Now each wire contribute mu 0 I, that is each wire that is passing through the loop contribute mu 0 I, and those outside contribute nothing. Let us consider a loop and consider several straight wires carrying current that is passing through the loop. Some wires will not pass through the loop and they will not contribute anything. Thus we have a bundle of straight wires. Some wires are passing through the loop and each wire will contribute mu 0 I, and those outside will contribute nothing. Now in this case, the line integral b dot dl, the line integral b dot dl becomes mu 0 I enclosed. Closed integral b dot dl, which is equal to mu 0 I enclosed, where I enclosed stands for the total current enclosed by the integration path. The total current enclosed by the integration path, that is given by I enclosed. Now in the present case, as shown in the figure, the total current enclosed by the loop is I1, I2, I3, I4 and I5. Thus, closed integral B dot dl, that is equal to mu 0 I enclosed. This is the integral version of Ampere's law. Closed integral B dot dl, this is equal to mu 0 I enclosed. This is called Ampere law in integral form. Integral version of Ampere's law. Next is the statement of Ampere's circuital law. What is the statement of Ampere's law? We have seen that closed integral B dot dl equal to mu 0 I enclosed. So the Ampere's theorem states that the line integral of the magnetic field, Ampere's theorem states that the line integral of the magnetic field around any closed path is equal to mu 0 times the current enclosed by the path. Mu 0 times the current enclosed by the path. The line integral of the magnetic field around any closed path, that is closed integral B dot dl, is equal to mu 0 times the current enclosed by the path, that is mu 0 I enclosed. That is by Ampere's law, closed integral B dot dl equal to mu 0 I enclosed. This is the integral version of the Ampere's law. Now let us see the differential form of Ampere's law. We have seen Gauss's law in integral form and differential form. In the same way, we have Ampere's law in integral form and differential form. The integral form is closed integral B dot dl equal to mu 0 I enclosed. Now what is the differential form of Ampere's law? Suppose the charge is flowing in a three-dimensional region, then we can describe the current by the volume current density J. What is J? J is di by dA perpendicular that we have seen. So in general, if the flow of charge is represented by a volume current density J, then we can write J is equal to di by dA. Or I is equal to integral J dot dA. We can represent the current I as integral J dot dA. Now if the current enclosed by the loop is I enclosed, if I enclosed is the total current enclosed by the circular loop, then Ampere's law becomes if I enclosed is the total current enclosed by the loop, then we can write I enclosed is equal to J dot dA. This is the general expression for I if the current flows over a three-dimensional region, I enclosed equal to J dot dA, where J is the volume current density. Now, the Ampere law becomes closed integral B dot dl, and which is equal to mu 0 I enclosed, and that will become closed integral B dot dl equal to mu 0. What is I enclosed? Integral J dot dA. Here the integration is over the surface, so we can say mu 0 integral over S J dot dA. Let it be the equation number 1. Now, using Stokes' theorem, closed integral B dot dl, that is equal to surface integral del cross B dA. Put it as equation number 2. Now, 1 in 2 gives del cross B dot dA, which is equal to mu 0 J dA. From this, you will get del cross B, which is equal to mu 0 J. This del cross B is equal to mu 0 J is called the Ampere's law in differential form.